So one can model the cells as population of some population of some species, but how one can model the arteries, etc. So these are some challenges. You can see this is a real structure inside. So it's not very user friendly to model all the key ingredient of tumor. So that's not very easy task. Okay. Yeah, for example, if you see the structure, individual cells, these are the tumor cells up to 65%. Vasculature means the pipes type. These are network up to 5%. Then interstitium, so the remaining empty space, that is up to 35%. So these are on the maximum side. Now, if you classify in vitro analogous and in vivo analogous, so that means one can treat tumor as sitting inside the body, or one can treat that it is in vivo. That means it is completely outside. Inside is surrounded by tissue, in vivo, and in vitro is completely outside. So when I say completely outside, for experimental considerations, a tumor is grown in, let us say, mice or a rat, and then that is taken out with some vessels still attached, and then experiment is done, and then again put it back into the mice for experimentation. So that is in vitro and in vivo. So now, how the dynamics are controlled, the tumor dynamics. So typically the cell doubling, through cell doubling, the tumor grows. What do you mean by cell doubling? You have few cells, then they are growing number. So that is the exponential growth model. These are general dynamics. But sometimes it may not be exponential. There may be other factors which are slowing down the process. So that is the next model. Then tumor is spreading and invasion completely. So that is the complete complex dynamic model. So we will review these three models one after the other. So when you say mathematical modeling related to tumor, fundamentally is studying the growth, that is a large time scale. Then transport of drugs and other blood-borne solute molecules, that is the transport scale, that is a short time scale, and identifying critical issues based on parameters. This is the aim of mathematical modeling. There are two approaches. One is the discrete approach. When I say discrete approach, it is like individual cell population, whereas continuum approach is on the global scale, large scale, macroscopic. It's not discrete. We will see the complete tumor structure as a continuum. That means it's a large scale, one entity. So there is a difference of this approach versus this approach. What is that? You will see very soon. So when we talk about any population models, the typical evolution in the dynamical system approach, people talk about Maltose models. So what is the Maltose model? Maltose model is applicable to any typical growth of population. So those who have studied dynamical systems, prey, predator modeling, etc., they would have come across these Maltose models. This is due to Thomas Robert Malthus. What are the key assumptions? Population is homogeneous and it is isolated, so not influenced by other species. Then resources are also not influenced by external factors. That means there are sufficient resources and only population can influence, and a very large population. So we are not considering any disturbances, random processes, etc. So under these, very simple model of any population growth is based on the following ordinary differential equation. Here C denotes the cell density. C denotes the cell density or any population density for that matter. So the growth rate of change of the cell density or population density depends on two factors, alpha and beta. So where alpha, we assume alpha and beta are positive, both positive. So one is aiding the population, another is retarding the population, therefore a negative sign. But both are proportional to, essentially proportional to the population size. That means there is no other, nobody else is influencing, only the population themselves, how they are reproduced, how they are killing each other, everything is within the population. So you can pull out alpha, beta and call it some lambda. So it's a simple model. When alpha is less than beta, you have, so that means enough production is not taking place, whereas enough death is taking place. So therefore, you can see the population is decreasing, whereas alpha greater than, then the population is increasing. So then the next model is, okay, you cannot have always such an idealistic scenario. That means one population is depending only on its own. That's not possible. No, there are several other factors. So the first and simplest factor is proposed by Verhulst. So P.R.A. Francois Verhulst suggested that for each population growth, it is not unlimited, that exponentially it is growing. There are some carrying capacity. Given the conditions, there are carrying capacity. Population growth is controlled by such carrying capacity. Okay. So what is the carrying capacity? For example, it could be population is growing. If you do not consider the, let us say, the seasonal effects, then simply go for exponential model. Maybe you will get wrong results, right? You may have to consider the seasonal changes. So then you take the maximum of in each season. So there is a carrying capacity depending on the season. Okay, so that is one factor, things like that. So accordingly, if you consider, so carrying capacity of any environment is the maximum population size which can be achieved within that given resources. So that is the carrying capacity. That means there is a limitation. Initial growth is very slow, and as time progresses, in the middle there is a drastic growth. Then once equilibrium, then population remains constant. So this is of course given resources, only the given resources. Okay, so this is called logistic growth. Okay, so now the dynamic model. So what is the dynamic model is saying? Okay, so the logistic growth is dynamic. So when I say that, here the lambda, earlier model, whatever lambda is now function of the population, and if k is the carrying capacity, you can get this model. Now if you have unlimited carrying capacity, then it will this term goes to 0 and you will get the Maltose model. Okay, if you have unlimited, k goes to infinity, we go back to the Maltose model. So this is a dynamic growth. Where is the dynamic growth? You see the lambda. If lambda is 0.25, then population growth is a little, takes some time and to reach the equilibrium. If lambda is 0.5, then if lambda is 0.75, very fast. Okay, so this is a dynamic carrying capacity model due to Verhulst. Okay, so this can be easily adapted to the cell growth of tumor. So that is the idea. Now the next improved version is Hammenfeld model. So here what they identified, okay, you are saying carrying capacity is constant, but it might be changing due to the dynamic vasculature. So K is not constant. They have obtained this following correlation. What is the correlation? Vasculature. Vasculature is nothing but inside the tumor, the pipes, the density of pipes. and these pipes will change. Why? Because as time progresses, the cells inside the tumor, the tissue, etc., die. It becomes necrotic. Therefore, there is no sufficient nutrient. So the vasculature density will become compressed. As a result, the carrying capacity is dynamic. So the rate of change is correlated like this. Of course, it depends on the cell density, where phi is rate of angiogenesis stimulation. Okay, so once you have a tumor, you try to give some medication, then the previously generated vasculature, so that has its own natural growth. So that is nonlinear growth. So these correlations have been proposed by Hammenfeld model. So this is one approach. Combining these two, the dynamic growth model, the rate of change of cell population inside a tumor is following such structure where the carrying capacity is dynamic. Okay. So in the previous slide, we have seen the carrying capacity is depending on the population as well as its own previously generated vasculature. But once some human is identified with cancer, people go for various treatment, right? Various kind of treatment. So immunotherapy, chemotherapy, etc. So as a result of that, the cells will be affected. When I say cells will be affected, sometimes the healthy cells also affected, and many times the chemo is to kill the cancerous cells. Therefore, the chemo also influences the carrying capacity. So this additional factor is used. This acts as the carrying capacity controller due to the chemotherapy, and where G is the chemo function. Okay, so this is some kind of good function. That means controlling the because you see carrying capacity is reducing. Okay, so this is due to the chemo. So correspondingly, you can see how the population is. This is the fast growing. Okay, but it is with the chemo, it's a slow growing kind of a scenario. Okay, so these are all differential equation, ordinary differential equation approaches. So now what is the drawback of this Ode approach? The drawback of Ode approach is lack of spatial information. That means you do not have any space information. But typically what happens in tumors, primary tumors are in one location, and if it is not treated, there will be signaling through various macromolecules. Then there will be secondary tumors inside the body at some other location. So in all these models, we have only time information. There is no spatial information. When I say spatial information, location dependent. That is not there. So if you want to combine the dynamic growth as well as spatial information, then Ode approach is not sufficient, because Ode is only one independent variable. But when you talk about the space, then you have another variable. Hence, we have to move to Pde approach. Okay. So when you talk about Pde approach, the rate of change of tumor cell population is a natural diffusion process of the population. Okay. Plus the net proliferation of tumor cells. When I say proliferation, so they are due to the kinematic dynamics. That means it is like some external process, hidden process is driving. That is the proliferation and diffusion. So this is due to J.D. Murray. So the nice book by J.D. Murray, Mathematical Biology. Those who are interested, they can go through. So here C denotes the tumor cell density. For the first time, we are bringing spatial information. So J is the diffusion flux and lambda is the net proliferation rate. So therefore, this model is telling that rate of change of tumor cells depends on the diffusion flux plus the net proliferation. Okay. So where J is the diffusion flux. But what are the typical models of diffusion flux? Typical models are fixed diffusion. Those who have studied even +2 level chemistry, they can figure out Fick's law of diffusion or Kirchhoff's law in physics. What is that? J or Q is D times gradient of C. Okay. So the diffusion coefficient. So this is the active motility. Okay. Diffusion coefficient. What is diffusion? Suppose you in a still water, you put some drop of ink, still you will see the ink is spreading. That is the diffusion. So in that sense, no disturbances, no external disturbances, but still the population is changing. That is the diffusion motility. Okay, the cells are growing on their own. So that is diffusion. So if you plug in J is D grad C, you will get this equation. And lambda C, we have, this is the proliferation. Now if D is constant, then you get this. Okay. So this is, those who have done first course of PDE, they would have come across this type of equation. Okay, parabolic. If lambda is 0, this is a typical example of unsteady heat conduction, which is a parabolic equation. And one can, since it is linear, one can start attempting solutions using your separation of variables approach. Okay. So now, spread of muskrats. Similar diffusion process was used to predict the spread of muskrats. Okay, in this evolution models. So here, if you assume that at time t equal to 0, these are the population of muskrats, then this model drives at a particular time, what is the population? So where R is a typical growth rate, okay, and D is the diffusion coefficient. So now, since I said this is a linear model, people can get the solution, which is of this form, Gaussian type distribution. The solution is very much available. Okay, one can, because it's linear equation, somebody try using separation of variables, etc. They can try to get the solution. Okay, so linear model. So this is Gaussian type distribution. So the evolution, what is happening, we had discussed about Ode approach, but if you want to capture the spatial information, then you have to follow the Pde approach. So this is the simplest model which can be used to talk about spread of some species. That means how the evolution models are used to understand the growth of tumors. So that's an interesting thing. Okay. See, what I'm trying to tell you is typical dynamical system approach is very popular for estimating the growth of any population. Suppose people do survey. Earlier, when we were when we were children, we used to know about Indian sparrow, that is called Ora Pichuka in Telugu. That used to be plenty within our vicinity. But nowadays, if you see within your vicinity, it's very difficult to see such Indian sparrow. How it has become extinct. So people can fit such dynamical system models to predict the growth rate of any species or death rate, how it is evolving, how it is dying, etc. Okay, those kind of things. So now, same Fickian diffusion model 1D. That means the Laplacian operator. This is Laplace operator. That in one-dimensional radial, it will be this. So you can think of r equal to 1 is the boundary of the small circle, and we want to see within this how the species is changing, and with an initial condition. Yeah, it's a simple exercise one can solve. Okay, so sometimes your diffusion can be spatial dependent. So instead of constant diffusion, diffusion D can be spatial dependent. So then it will be sitting inside the divergence. Otherwise, if it is constant, it will come out. In any case, there is a competition between lambda by D. Why? What is D? It is diffusion. That means in the absence of